Space, the final frontier. We gaze up at the stars, asking questions as old as humanity itself. Where did it all begin? The answer lies in a tale of cosmic proportions, the Big Bang Theory. Join me as we journey back to the very beginning of time. Imagine a universe smaller than an atom, unimaginably dense and hot. In a fraction of a second, this tiny point expanded at an incredible rate, an event we call cosmic inflation. Picture a balloon with dots drawn on it. As you inflate the balloon, the dots move farther apart, representing the expansion of the universe. The universe wasn't born into existence, rather, existence itself was born. The Big Bang Theory is a triumph of science, but it's not without its mysteries. What triggered this incredible event? What existed before the singularity? We may never have all the answers, but that's part of the beauty of science. So buckle up as we dive headfirst into the fascinating world of the Big Bang. Picture this. The universe is a fraction of a second old, far smaller than an atom. It's a seething cauldron of energy, a cosmic soup hotter than any star. In this extreme environment, the laws of physics as we know them are still being written. Space expands at an unimaginable rate, a concept that bends our everyday understanding of physics. This period, known as the Planck epoch, remains shrouded in mystery. However, we do know this. The universe is in a state of rapid expansion and cooling. As it expands, the energy density decreases, setting the stage for the emergence of the fundamental forces in particles. Let's journey further into this incredible saga of cosmic evolution. The universe is now a tiny fraction of a second old, but it's about to undergo a dramatic transformation. Cosmic inflation. Imagine a balloon suddenly inflating to 1 billion times its size in a fraction of a second. Cosmic inflation smoothed out the fabric of space-time, explaining why the universe appears remarkably uniform in all directions. This rapid expansion was crucial for the formation of the universe as we know it. Cosmic inflation remains a cornerstone of modern cosmology. The universe is cooling, but it's still unbelievably hot. As the universe expands and cools, energy begins to condense into matter, guided by the fundamental forces of nature. First comes gravity, the weakest but most far-reaching force. Then the strong nuclear force emerges, binding quarks together to form protons and neutrons. Following closely is the weak nuclear force, responsible for radioactive decay. Finally, the electromagnetic force, responsible for light, electricity, and magnetism, separates from the other forces. As the universe continues to cool, tiny fluctuations in the energy density of the early universe begin to play a crucial role. These fluctuations act like seeds, creating regions where matter is slightly more concentrated than others. Gravity takes hold of these over-dense regions, pulling in more and more matter. These regions become the seeds of galaxies and galaxy clusters. The universe, now 1 billionth of a second old, resembles a cosmic particle accelerator. As the universe continues its rapid expansion and cooling, energy begins to condense into matter. This is the realm of fundamental particles, the building blocks of everything we know. Quarks, the quirky characters destined to form protons and neutrons, flit about. Leptons, a more aloof bunch that includes electrons and their elusive cousins. Neutrinos, zip through the crowd. And let's not forget the bosons, the force carriers, mediating interactions between these fundamental particles. As the universe cools further, the energy of these particles decreases. The stage is set for the next act in this cosmic drama, the formation of protons and neutrons. The universe has now cooled to a balmy quadrillion degrees. At this energy level, the strong nuclear force comes into play. Quarks can no longer resist its pull. 2 up quarks and 1 down quark come together to form a positively charged proton. Conversely, 2 down quarks and 1 up quark unite to form a neutron. These protons and neutrons, collectively known as nucleons, are the heavyweights of the atom. The strong force binds them together with incredible strength. However, the universe is still too hot for these nucleons to form stable atoms. While quarks are busy forming protons and neutrons, another group of particles, the leptons, are also making their presence felt. Leptons come in 6 flavors, but the most familiar to us is the electron. Electrons are much lighter than quarks and interact with the electromagnetic force. In the hot, dense environment of the early universe, electrons are constantly interacting with photons. Alongside electrons, another type of lepton plays a crucial role: the neutrino. Neutrinos are ghostly particles, almost massless and interacting very weakly with other matter. They influence how matter clumps together to form galaxies. The stage is almost set for the formation of the first atoms. The universe is now about 380,000 years old. The temperature has dropped to a relatively cool 3,000 degrees Kelvin. Before this era, the universe was a hot, dense plasma, a sea of charged particles. But as the universe cooled, a dramatic shift occurred. Protons could now capture the negatively charged electrons, forming the first stable atoms of hydrogen. This process, known as recombination, marked a turning point in the universe's history. The universe was now populated by neutral atoms, which interacted much less frequently with photons. Imagine a crowded room suddenly emptying out, leaving space for everyone to move freely. That's what happened to photons during the era of recombination. The universe, once opaque like a dense fog, became transparent. This freed radiation, known as the cosmic microwave background, is a faint afterglow of the Big Bang. The formation of atoms marked a crucial step in the evolution of the universe. The era of recombination wasn't just about the formation of atoms, it was a cosmic makeover. Imagine the universe as a stage, initially shrouded in a thick curtain of charged particles. As the universe cooled, the curtain began to lift. Photons, once trapped in the dense plasma, were finally free to stream across the cosmos. The cosmic microwave background represents the moment when the curtain finally lifted. With matter and radiation no longer in constant interaction, gravity could begin to exert its influence more effectively. The universe, now transparent, entered a period known as the Cosmic Dark Ages. Despite the name, this era wasn't filled with darkness in the traditional sense. The cosmic microwave background radiation bathed the universe in a faint, uniform glow. However, there were no stars, no galaxies, no sources of light other than the fading embers of the Big Bang. The universe was a vast, cold expanse of mostly hydrogen and helium gas. Within the cold, dark clouds of gas, gravity was at work, pulling together matter. The cosmic dark ages lasted for hundreds of millions of years, a silent prelude to the brilliant cosmic dawn that was to follow. First light. The cosmic renaissance. The universe, shrouded in darkness for eons, was about to experience a magnificent transformation. Imagine a canvas, vast and black, awaiting the artist's touch. The artist in this case was gravity, patiently sculpting the universe, drawing together clouds of hydrogen and helium gas. These clouds, cold and dark, held the potential for extraordinary brilliance. As gravity pulled the gas inward, compressing it tighter and tighter, temperatures within these clouds soared. Finally, after hundreds of millions of years of cosmic gestation, the critical threshold was reached. The intense pressure and heat at the cores of these collapsing clouds ignited the first nuclear fusion reactions. Hydrogen atoms, the simplest and most abundant element in the universe, fused together to form helium, releasing a tremendous amount of energy in the process. This energy, radiating outward from these newborn stars, pierced the surrounding darkness, marking the end of the cosmic dark ages and the dawn of a new era in the universe's evolution. The first stars were unlike any we see today. They were colossal, hundreds of times more massive than our sun, and burned with a ferocious intensity, their light blazing blue-white hot. These stellar pioneers, short-lived but immensely powerful, would shape the universe in ways we are only beginning to understand. Stellar nurseries, the birth of stars. The ignition of the first stars was not a singular event but rather the beginning of a continuous process that continues to this day. Across the universe, within vast clouds of gas and dust known as nebulae, gravity continued its relentless work, pulling matter together, igniting new generations of stars. These stellar nurseries, some spanning hundreds of light-years across, became the cradles of stars, each one a testament to the universe's remarkable ability to create complexity from simplicity. Within these nebulae, a delicate dance between gravity, pressure, and magnetic fields governs the process of star formation. As clouds of gas collapse, they fragment into smaller, denser clumps. These clumps, drawn together by gravity, spin faster and faster as they contract, forming protostars, the precursors to fully fledged stars. As material continues to fall onto these protostars, their cores heat up, eventually reaching the temperatures and pressures required for nuclear fusion to begin. The birth of a star is a violent and chaotic process, marked by powerful outflows of radiation and stellar winds that sculpt and shape the surrounding nebula. Yet, amidst this cosmic turmoil, a delicate balance is struck, allowing stars to shine brightly for millions, billions, or even trillions of years. Galactic Genesis islands of stars emerge. As stars ignited across the cosmos, they did not remain isolated. Gravity, the architect of the universe, continued to draw them together, shaping them into vast swirling collections of stars, gas, dust, and dark matter galaxies. The formation of galaxies is a complex process, influenced by an interplay of factors including gravity, the distribution of dark matter, and the energy released by supernovae, the explosive deaths of massive stars. Over billions of years, galaxies evolved and diversified, taking on a variety of shapes and sizes. Some galaxies, like our own Milky Way, formed into majestic spirals, their arms adorned with billions of stars and glowing nebulae. Others coalesced into elliptical galaxies, smooth and spherical, their stars orbiting a central bulge. And still, others took on irregular shapes, sculpted by the gravitational tugs of their galactic neighbors. Within these galactic islands, stars lived out their lives, fusing hydrogen into helium and heavier elements in their cores. The heavier elements, forged in the nuclear furnaces of stars, were scattered back into the interstellar medium through stellar winds and supernova explosions, enriching the material from which future generations of stars would form. Cosmic evolution, from Big Bang to now. From the initial singularity to the formation of galaxies, the universe has transformed over 13.8 billion years. Driven by expansion, gravity, and star evolution, the cosmos reveals new wonders. The universe today is a tapestry woven from its past. The chemical composition of stars and the existence of planets are products of the Big Bang. Exploring the universe, we appreciate the interconnectedness of all things. The atoms in our bodies were forged in long-dead stars, products of a cosmic cycle of birth, death, and renewal. The story of the universe is still being written. We gain a profound understanding of our place in the cosmos, realizing we are all connected through space and time. A universe in motion. We've journeyed together from a point smaller than an atom to the vast cosmic web of galaxies that exist today. It's a story of incredible change, of expansion, cooling, and the emergence of structure from a seemingly chaotic beginning. The Big Bang Theory, while still being refined and explored, offers a compelling narrative of how our universe came to be. But the story doesn't end there. The universe is not static. It's a dynamic, ever-evolving entity. Galaxies are constantly on the move, sometimes colliding in spectacular displays of cosmic fireworks. Stars are born, live out their lives, and die, seeding the interstellar medium with the elements that will form future generations of stars and planets. And somewhere, on at least one of those planets, life emerged, looked up at the stars and wondered, how did it all begin? We are those life forms, driven by curiosity and a thirst for knowledge. We are the universe trying to understand itself. Pondering the cosmos. The Big Bang Theory is a testament to the power of human ingenuity, our ability to piece together the history of the universe using the tools of science and mathematics. It's a story that fills us with awe and wonder, reminding us of the vastness of the cosmos and the countless mysteries it still holds. What caused the Big Bang? What existed before the singularity? What is the ultimate fate of our universe? These are questions that continue to captivate scientists and philosophers alike. While we may never have all the answers, the pursuit of knowledge, the drive to explore and understand, is at the heart of what makes us human. So, the next time you gaze up at a starry night sky, remember the incredible journey that brought us here, from the Big Bang to the present moment. Share this story with others, spark their curiosity, and encourage them to ponder the grand mysteries of the cosmos. And don't forget to leave your thoughts and questions in the comments below. I'm eager to hear your perspectives on the universe's beginnings and what mysteries you find most intriguing. Keep looking up, keep asking questions, and never stop exploring the wonders of the universe we call home.